first colloquial speaker in IUCAA in summer of 1999. And since then, he has been visiting us. Well, in between, we had a COVID interval of about 5, 6 years. But now we are again back to almost normal. So we look forward to your visits and now to Colloquium. Yeah. Very. Thank you, Naresh, very much for all these warm words. But, I must go back quite a few years. Now I'm really very happy. The Trinity are here. Naresh, Ajit, and Sanjeev. And as Naresh said, I came here in 1990, and it was a very pleasant visit. But also, I remember that day, colloquium day, very clearly, because that very early morning, Professor V.V. Dandekar Nardekar had passed away. And to my surprise, when my colloquium started, Professor Nardekar was there. So this requires a lot of guts to be in a colloquium. And I really miss Paddy, uh, who was so much younger to me. And in his office, we had to have these shadow fights, say like WW wrestling. But he was very lovable and very close to me. And Ayuka also has been very, very kind to me in more than one way. So as Naresh said, I'm visiting after about 7 years, I think. Okay. So if you take this as the periodicity, then probably this is my last visit. A 7 years periodicity. Okay. So I'm actually not, let us say, I'm not a committed party line string theorist because I never had a single course on string theory in my class. So whatever I learned by myself. And so my education of string theory by trial and error. But I think I have enjoyed working in this field. So let's see, when did I write my first paper? In 1985 December. So then I took a sabbatical during COVID from string theory, but now I'm still now returning to string theory. So you will find that I'm not going to advertise string theory. Okay. So the title is an odd story. So you have to wait till the end to find out what is so odd about it. And I assume that there are no string theorists in the audience. So whatever will be there will be minimal. Okay. And so this is actually the narration of a symmetry of string theory, but this is a very special to string theory. You do not see this kind of symmetry in quantum field theory at any level. The reason is string is a one-dimensional object. Okay, so there is something which is special to this one-dimensional object, the extended object. Second thing that I want to say is that it is very bizarre that uh, if a string is one-dimensional object, it is moving in, in flat space-time. So, like if it is like this, so as it will move, it will trace on the surface. So if you want quantum consistency condition, then a bosonic string only is consistently defined in 26 dimensions and a fermionic string in 10 dimensions. Okay. And as I said, the target rate. So if you take a point particle moving in space time, okay, but it doesn't say what should be the dimensionality of space time. Right? A point particle will trace a line, the wall line, and it can move in any sort of uh, dimensions. It is very peculiar to string theory. Okay, but we live in four dimensions. There is no doubt about it. It'll take 5 minutes off, not even 5 minutes. So in the very early days, it's actually a true incident. Very early in this days of string theory, 1985, by a very young man, okay, 20-year-old man, he wanted to do a master thesis in Geneva with Gatto, who is very distinguished physicist, and he wanted to work on string theory. And Gatto said, I don't work in string theory. I cannot guide you. He said, no, no, you just be my guide. Okay. So then he worked out all this, everything. Then his father actually is a permanent staff in Spain at the least. So he was explaining his father about string theory late in the night. So finally, boy was very delighted that he had proved E equal to 26. So then his father meekly asked, oh, son, I am an experimentalist. I do experiments and we know space-time is four dimensional. So what 26 has to do with physics? So the boy, is trying very hard for 2 hours and he's exhausted. Then he throws up, that's about physics. Good. So these are the good old days, okay? I think it is not so bad. But coming back to four dimensions, so but 1925, I think. Anusa and Klein, okay, separated by couple of years, they actually started from Einstein's five-dimensional general theory of relativity and then said, let one dimension be compact, circle, and that radius is very small. Then what did they find? They found that in four dimensions, there is general theory of relativity of four dimensions, and there is vector field, and which electromagnetism. So they are very delighted. And they said that R is so small that both these experiments cannot probe that radius. But very unfortunately, when tried to fix the numbers, it did not work out properly. For example, they could not reproduce the mass of the electron from this calculation. Okay? But when the string theorists actually saw this, 26, so they were delighted. Now, intervening period, since 70s, we fairly know the what is called standard model. It is SU3 cross SU2 cross E1, okay? And SU2 cross E1 is the unification of electromagnetism and weak interaction, and SU3 is the force for the strong interaction. And today, if you look at experimental data from CERN and other places, actually the level of accuracy is amazing. Okay, really, it's very, very sort of glorified situation that a theory can explain experiments what science. Okay, so question is we should actually sit down and say, okay, that's it. But then people were a little bit ambitious. They introduced what is called grand unified theory. So a theory which incorporates these three gates. Okay? So one of the predictions of what was that proton is unstable. But it is a very good idea. You see, if proton is unstable, and if you go back to Sakharov's three principles, then you need instability of proton is actually the violation of barrier number, that there will be barrier asymmetry in the cosmology. Okay, today. So you excited. So but then proton should be unstable. But so far there is no evidence for instability of proton. So there is not really experimental evidence that there is a grand unified theory. But people are still carrying on. And there are other attempts, but But there is one feeble evidence that maybe this theory is unified at 10 to the power 16 GeV in contrast to electronic unification, which is at 1 TeV. But you know, this evidence is not really clinching. All right. So, so superstring theory is expected to unify the four forces of nature that includes the gravity. Not only that, actually perturbatively. Actually, gravity is finite in the whole universe level, which is a big thing. Okay. And then from fact that the conservation laws associated with various currents is actually valid, is only true. Okay. In for gauge groups, which is SO32, for gauge groups, which is E8 cross E8. But that was actually proved by Green and Schwartz before, let's say, the so-called string revolution started, because in a few months' time, actually, people produced a string theory model which only admits the things together, which is very big boost. That out of all choices, only two were available, naturally. But this is in 10 dimensions. So immediately people actually started arguing, let's go back to Kaluza and Klein and assume that extra dimensions are compactified on their small radius. But then experimentally there is no evidence of the extra compact dimension so far. But this is not the only one. Other theories like supergravity theories also admit higher dimension theories. And strictly speaking, today there is no experimental evidence for string theory. In this sense, when physicists say experimental evidence, go and open that little data book. So at data book, if something is listed, if it is not listed, okay, in that sense, supersymmetry is also not discovered. Okay, so then the question arises hmm, that you see, let's say 1984, August, right? 40 years, right? Why we have survived and still you find papers written. So what is the reason? Okay. And so keep asking questions in physics, basic questions. So all those, as I told you, standard model is so well established in the sense that the predictions of standard model agree so well with experiments, but there are questions to be asked. Okay. And question is why fermions have these masses? Electron has zero point 0.5 MeV and muon has, let's say, 100 MeV and the electron has 1.6 GeV. Okay. In some estimates, UD equals 150 MeV and so on, and top quark is 180 GeV, like rough. Well, and of course, in standard model, why it becomes that is because you give vacuum expectation value to the Higgs, and those couplings actually produce uh, the equal couplings produce the masses. But those are all arbitrary parameters. They have to be put by hand. So I don't remember, depending on whom you talk to, standard model actually described by 21 parameters or 27 parameters, well, what you count as parameters. But it is that large. So, and then it is not the only question. So why the gauge couplings are what they are? Okay. Uh, Is it the some kind of satwa that we cannot ask this kind of question? Okay. So dark matter is experimentally observed. Okay. We know that dark matter exists, but what is dark matter? There is no answer. Then mother of all questions is dark energy. In other words, the cosmological constant. So people argue, the quantum gravity people, string theory people argue that the origin of cosmological constant lies in uh, quantum gravity effect. But what it is, what is this effect? Okay, if you check, okay, I don't think people will agree. In the sense, people agree that electron mass is zero point 0.5 MeV, okay, or the G minus 2 is computed to 9 places in decimal, okay. But is there something that everybody accepts that yes, this is a number which is experimental measure, and this is the theory which actually predicts this number, and what will be degree of. So this is, I consider, sometimes people think I am arrogant, but I think cosmological constant problem is an outstanding problem in physics. It's not at all easy. But those who know, please check the papers of Edward Whittle, how many papers he has written on cosmology are constant. It will not exceed three. It is not solved. No, no, but you see, there are questions like this. It is not that string theory can actually answer all these things. For example, another domain is the black hole. Okay, the black holes, as Bekenstein Hawking showed, have entropies. Okay, now that is a macroscopic derivation. But if you have a microscopic theory, then in statistical mechanics, entropy is computed from a statistical mechanical point of view. Actually, it counts the number of degrees of freedom in statistical mechanics. So, if string theory is sort of, let's say, advertised as a quantum theory of gravity, then you should be able to calculate the microscopic entropy. So two things. One is Bekenstein Hawking formula. Another you have statistical mechanics of that. You compare the two sides. Not all for black holes, but for a class of black holes which arise as a solution to string theory, you can actually uh, count them. And there is one paper by Amit Das and Samir Mathur, which actually fixes the prefactor of that. Because I'm talking about the prefactor of that, actually fixed from string theory, ab initio. So, which is, I think, uh, something, And well, Hawking said that black holes are not eternally black, because black holes radiate, because of the quantum effect. So then, what happens, truly speaking, if you say, when we are behind the horizon, then Hawking radiation comes out, but it's a formal radiation. So it cannot be expanded in a plane wave. So there is conflict with unitarity that probability is not conserved. So, so therefore, the question arises: if you have string theory, you have Hermitian, Hamiltonian, okay, then can you actually compute the Hawking radiation distribution of Hawking? But this has been also done for a class of black holes, okay, rather successfully. So, truly speaking, so in physics, the idea is not to have add-on, okay, but we try to understand as much as possible. Simple example is when Bohr came with Bohr model. So electrons are going in a circle, then you found the spectral lines were split. So first attempt was to go for the elliptic orbit. But then that was not the path to follow. Okay. But only when Schrodinger equation was involved and the quantum mechanics developed, then you can understand spectral lines. Okay. It's like that. Okay. You don't understand everything, but you can understand without. As I said, but string theory, some people uh, actually in early days they were so over enthusiastic. Okay. So I was in 85, 86 at some the young postdocs, okay, my friend will come from there. So excited, all the time they're excited. Okay. And when they're talking, we are there. Hmm. We're around the corner. We'll be there. This is the kind of thing postdocs are talking. So somebody says, we'll be able to calculate the muon mass. So I met Sandeep a few months ago. So we met and I asked Sandeep, see, what are you doing? I'm doing this. I said, but you are saying that we are on the corner and we'll calculate muon mass. Have you calculated muon mass? So Sandeep's reply is very amusing. Also, we are in, yes, but not in my lifetime. So it is the optimistic part of string theory. Yes. No, no, no. So that is a little bit more. This Hawking field. So that because it is strumming of a did, but okay, there are a few loose ends. So, but then I think there is this paper of Strominger and Mallasana. But really, the people who really fixed it, ab initio to say, is Sumit. And because Hawking actually mentions in one of his papers, that's amusing that Das and Mathura fixed this refactor. So, okay. So, so this one thing that goes into many of the things in string theory, including Strominger and many other things, is duality symmetry. And very naive. In fact, there are two kinds of duality. One is S-duality, which is strong, weak duality, and it takes strong coupling theory, weak coupling theory, or vice versa. It could be different theories. Best example is magnetic mono. So you say we have not seen magnetic mono. So Dirac's charge quantization condition tells us that if we are living in QED today, okay, then suppose there is a QMD, magnetodynamics, then us we are fine structure constant. But in the S duality, that will go to magnetic fine structure constant. See, we is 1 over 137 today, but that theory were 137. So in parentheses, you can actually see that if we are doing perturbation theory to count, find the splitting of hydrogen spectrum. Okay, you can't do that for magnetic hydrogen atom if it exists. The other one is so what target space duality. That is where the story begins. Okay, so I think I spent a lot of time on. Okay, so I'll give you a very express introduction to string theory. Okay, is one-dimensional object moves in d dimensions. Okay, if there is a string, it has two possibilities. Two ends are open or two ends are joined. So the open strings and closed strings. Now, since the one-dimensional object, the three-string equation solution is a wave equation. And so one can go like this, other one can go like this, one can split as left and right mover. Okay? This is trivial. This has nothing to do with string theory. Really. So we can expand them in Fourier modes as we do in acoustics. Okay? So there will be center of mass coordinate, and there will be center of momentum, and then the oscillators. We have all learned this. This is nothing to with really hardcore string theory. So since string is one-dimensional object, as it moves, okay, suppose it moves like this, it will sweep a surface. Okay? So for the particle, it is a line, it's a surface, so there has to be some kind of a three factor which has dimension. But what is important is all can be calculated by you in your mind. So the canonical Hamiltonian is p square plus because it depends on other coordinate x prime square. So you see, very simple thing that you see if you interchange x plus p and x prime, if you interchange, then the Hamiltonian is like ah p square plus x prime square. Right. So suppose the star goes this way, sigma goes this way, you integrate which one? Actually, sigma is actually interchange. So I have a string that two particles are scattering the strings, so it was like a surface. Okay? So it was like this. If you interchange, so it was like this. But still, it will describe the same physics. And not only that, the spectrum of the two Hamiltonian they will be same. So this is the simplest T dual. Well, yeah, that's a T duality invariance. Okay. Now, suppose we consider the string in the background of constant P and G. That means antisymmetric tensor also. So that will be I not this diamond, but this is sort of message. This also leads to sigma, and then it is constant. You x dot mu x dot mu plus epsilon alpha beta. Okay? X three alpha beta. Okay? Alpha beta d alpha x mu beta x mu x mu. So this is not you can do it yourself. That what is the canonical momentum associated? Canonical momentum would be Hamiltonian. Is you say I have shown this. Okay. Yes. Yes. Now, just calculate it. Eliminate the time derivative with momentum. So you will see something like this. Now, I have explained that you see, canonical Hamilton is W to M W and M is this matrix. This is symmetric. You can check. This is symmetric. This product is anti-symmetric. You can transpose. So, it's symmetric and this is symmetric. This is symmetric. Okay. So, so this is the sort of first simplest example of duality. Okay, in the sense there is an underlying symmetry associated with. You see, the Hamiltonian can be expressed. Okay, this Hamiltonian is invariant under m going to omega m omega transpose, and this is a, eta is the d comma d metric, and these are unit d cross d matrices. Okay, so these are non-compatible. Let's not go into all this. All this. So here also the string spectrum is duality invariant. So you see, we started with very simple configurations and we getting into a little bit more complications. Now let's go to a little bit next level of complications. Let's that this metric and antisymmetric tensor depends on the time coordinate. That means x0. Well, but it cannot be trivial, but we can do some clever manipulation. I can do it, so you can do it. It's not a big deal. But then you see, you will find the equation of some person are d minus 1 or d minus 1 over here. Okay? So because the time coordinate takes out 1, so therefore there is this invariance. Okay. It's like a time translation theory. No, no, it's a little bit more than that. Because you see, when you have a matrix which has only time dependence, you can make some scaling and general coordinate transformations to make the so let's say 0 component you can set to 0. So it is basically d minus 1 cross d minus 1 metric. And because the antisymmetric tensor is antisymmetric, so all the diagonals are 0, then there is a gauge symmetry associated with this potential. So that actually can make it this again d minus 1 cross d minus 1 antisymmetric matrix. Matrix. Okay. So, but this is not so far. We come to the hard part little bit. So now the story becomes sort of a little bit non-trivial. So consider that we are in d hat dimension, could be 26, and then it's moving in a matrix g hat and antisymmetric torsion b hat, but such that this metric only depends on d dimensions. Okay, okay? 0, 1, d, and then d of the rest of the coordinates, they are isometric in the sense that all these tensors don't depend on that. Now, you just back of the envelope thing. You had G hat, you had D hat. It will go to what? It will go to G mu nu, that is the space time in D dimensions. And then you say G hat mu alpha is like a gauge field. Mu is a vector index and this is internal. So I call it A mu and then G alpha beta, which are scalars, to the lower dimensions, right? Similarly, antisymmetric tensor, it will go to B mu nu, which is a tensor in D dimensions, and B alpha mu, so this is a gauge field, and then B alpha beta to let us say intimidate the coordinates moduli, okay, then they already certain little bit. Okay, but this is the thing. So, so we have how many? 2D abelian gauge fields. Okay, and then there are d square, g plus this symmetric, this is antisymmetric. You sum them up. That d square are scalars. Okay, so G is symmetric matrix and B is antisymmetric. So so this equations of motion, this is non-trivial. Okay, this is really non-trivial. But to express this as ODD, covariant equations of motion, that is, this is non-trivial. Okay, this is not so easy. So, so what happens? If these 2D of them, they actually transform. You can just imagine instead of OD comma D, you can think that this is O2D, right? So it will be rotation in two-dimensional space. So there are vectors under OD comma D, but this is not so easy to prove. But please accept that they actually parameterize uh, coset, which is OD comma D by OD cross OD. So if you make the counting, take the total number of this here, 2D square minus D, and then calculate what is the degree of freedom, take that out. So this counting actually works. All right. So now, yeah, I think I'll finish on that. Well, there is not much mathematics. Which I intentionally omitted maths. Now, we can think that you see, this was in flat space. Okay, so it is something like this. Let's suppose that target space was not flat. Okay, there's some geometry in it. Now there will be geminum, which is the metric, and there will be torsion. Okay, so you don't assume that it's torsion free. Then ordinarily we'll see d equal to 26 when everything is flat. Okay, so but then you see, I choose a coordinate system where it is like this. Okay? Anyone can choose a coordinate, two-dimensional coordinate system where when this string evolves, it will be like this. Right? There's no reason why it should be always like this. But when it will be physics, physics should be independent of this. Just like if you recall your electrodynamics, what is fundamental in electrodynamics, quantum electrodynamics as well as classical electrodynamics, is Gaussian. In quantum electrodynamics, it is the Gauss law constraint, which actually throws away the physical states. Okay? So it is exactly like that. If you remember this, if, if I can do it, all of you can do it. It's not a big deal. Okay? So, so when we write the action for Maxwell equations, okay, so we write in terms of for Maxwell Lagrangian, we write in terms of the field strength, not in terms of the potential. So that is gauge invariant, right? So here the analog of gauge invariance is this. Whether it is this or it is this. So that actually, because it is now some kind of a field theory. So, so all values of G and B are not permitted. There are only special values of this G and B which are permitted, like Gauss law constraint. So, but this constraint comes as a differential equation, just like Gauss law constraint. E dot B, okay, then is zero. But if your matter, that particularly for non-abelian, then covariant E dot covariant D dot E is something. Okay, it is exactly like that. But if you know a little bit of geometry, think in terms of electrodynamics or gauge theory, it is rather simple. Okay, so these differential equations are actually relating G, B, and other things. And so again, in fancy language, to keep people away, yeah, it is like giving some big Sanskrit sloka and say, you understand this, you don't understand that. Well, this is called the renormalization groupifications. Other the beta function associated with this has to vanish. So what is amazing? They two independent arguments, right? The beta function associated with this actually vanish. So you can work backwards and say, what is the a functional which will give me those differential equations? So that is the thing. You say, you write down an action, whose variation actually with respect to all these fields gives you the beta function equation. What is this action? You see, this is there is torsion, but this is actually the Einsteinic action in terms of matter field. So Einstein, the equation of motion derived from this actually coincides with the beta function equation. But nobody ordered in advance. Not anybody cooked it up, okay, in advance to find this. Okay, but this happens. Okay. So in fact, more if you use this action to find the scattering of stringy states, or you start with the fundamental word C to compute this scattering, so they are actually agreeing. Mhm. So there are all these things that actually which really we at a very deeper level we really don't understand. When I mean we, it is not that I have tapeworms in my stomach, but you know, kings and people with tapeworm use plural. Okay, we. So we mean a lot of people in this community really don't understand how the theory knows about this. Yeah, 26 is when you do, let's say, weak field expansion. So one will be D is equal to 26. The rest will be beta function equation, right? Both have to be fulfilled. One part is 26. Okay. So I'll be there. So now, you see, as I told you, that we had this and then we actually have some coordinates. We actually don't, backgrounds don't depend on those coordinates, all these things. So if we do same thing to this action, okay, same thing to this action, you see, this odd coincidence that starting from d hat dimensions, suppose we compactify this on torus, you are fine thing that actually the circles are small, simple things torus. Okay, so we compactified on this, and then the backgrounds don't depend on internal coordinates, which are the torus, y of so e of them. So now the manifold, which is to start with was d hat dimension, now it decomposes to md and pd, which is the torus. Okay. I hope this is not too much of high growth thing. Now I told you. Okay. Now in this again, so G hat is decomposed into G mu in D dimensions, the gauge field, then G alpha beta the scalars, okay, which are along the internal direction, but they don't depend on the internal coordinates. So D plus capital D plus D is D hat, and same thing with this. But you see, what is amazing? This is really amazed me. What is amazed me that original action can be actually decomposed to SGB phi, S of A, and X of M. So everything is SGB phi. This is in D space. Everything in D space time dimension is the scalar curvature in D dimensions. In the kinetic energy, there is a little bit of not cheating. I didn't want to be technical. So this is called shifted electron. And this is the portion in the no dimensions. So they have no heads. And this part, you see, I defined curly F. Okay. So this is M inverse. M I told you, and Fj. So this is the 2D of those gauge fields I introduced earlier. Okay. So what is important, you see, this depends on space-time coordinates, so it doesn't depend on internal coordinates. So whatever you do to the internal directions, nothing happens. Okay, that's invariant. And you see the way it is written. So this is a two D dimensional vector I told you. This is 2D dimensional, but so this runs from 1 to 2D. But this M, okay, I'll tell you in a moment. Okay? So M is the same matrix I introduced. Okay, but now it actually is space-time dependent. So this you can check. Okay, is that uh, so this is actually uh, ODD invariant, and then this eta I introduced, eta is the metric of ODD non-compact. Okay, so now as I told you. Sophistically, okay? Waving my hand so much that if you do this, you find this ODD symmetry and it's invariance. So, in summary, you see, they are tensors, so they don't depend on ODD indices. This is actually, is it? This is D of them, this is D of them from the torsion. So, there are 2D of them, okay? And then M is already ODD invariant. So, so therefore, you see, this is a symmetry of the action. There are two things. Suppose you found a solution to symmetry of this action, okay? A set of solution. In technical language, since they actually a solution to the equations of motion, they are termed as vacuum, ground state of the theory. Okay, in technical language. Now, so because of these invariants, if you actually implement one of these transformations on a solution, it will take you to another solution, which is actually solution to equation solution. But the two solutions are not equivalent. What is meaning of inequivalent solution? That on those solutions, you cannot actually take one to another by implementing general coordinate transformation or the base transformation. So this actually has industrial application. You don't get this. With DAE, we all get, well, not me, I'm retired, but those people get societal applications. Huh. I think there are at least 1,000 papers which are industrial applications. Because yes, you go back 10 years and you'll find. So, societal applications. So, so I'll ask a question. Heterotic string, okay, has most general black hole solutions of heterotic string is specified by how many parameters? Okay, the answer is 58. Why? Because heterotic string on one side is has 22 coordinates, other side has 10 coordinates. So when they come to 4 dimensions, so there will be 22 gauge fields on this side. Okay, there will be 6 gauge fields on this side. Okay, so 22 plus 6 is 28. So abelian gauge field. So there will be 28 electric charges. Simple. Yeah. But it requires association to do this. And then there are also magnetic counterparts. So 28 plus 28 is 56. And two parameters are angular momentum and mass. Okay, as simple as that. Now, so this is actually combined effects of going from one set of electric charge to another set of electric charge. More technical language is called a lattice. And then you use S-duality. That magnetic solution will be generated from the electric solution. Okay, so now that if you combine them, so you have 28 magnetic and 28 electric field. Okay, so this is quite amusing, right? Now, now you see, this is the question. It is possible he could have done it. Okay, but also it's possible he could not have done it. In the sense, if Chandrasekhar was just given the metric, okay, and these gauge fields exist, and Chandrasekhar was not aware that this T-duality, okay, and S-duality. Probably he can do it, but it's not very obvious that he can. Well, now a PhD student, after studying 6 months of T-duality, S-duality, actually do it. Then you have to go to Ashok's paper and then work it out, you get it. Okay? But not Ashok, but this, what is her name? Miriam Satich, okay, and the Chinese collaborator. They have actually empathy. So this is not all in. Oh, very good, very good. I'm very happy. Where is the organizer? He said, please stop in 50 minutes. So he's fled to Bombay. So anyway, so now we can do same thing with cosmology. Okay, not starting from a given cosmological solution where there is no, let's say, what is called exchange charge, but the person You can generate new solutions, okay, and so on. All right. So I'm there. So combined with S and T duality on string theories, formally, actually, you can relate various string theories. There are five of them. They look all different, but actually, various dimensions they can be related to each other. So people think that there is one underlying fundamental theory, okay, magic, membrane, one more, mystery, everything. Mother, okay. So theory, but there are evidences. The question is, what is M theory? Now, some of the people here in the audience, if they think very deeply, but this is a gamble, right? You are buying some stock and that company may go bankrupt. So you can actually write down M theory Lagrangian. If you write down M theory Lagrangian, then you will be immortal, right? This was action, okay? So this is quite a challenge. So, but I'll not go into all those things. That is actually completely. So, uh, so we discussed. So when we started with all this, did you guess that there will be a non-compact group? Okay, symmetry group. Okay, so and so many non-compact groups you encounter in physics. Lorentz group is non-compact, and complexified is SL2C. Beyond these two, in day-to-day affairs, when you go to buy vegetable or milk or say you don't fill up your petrol car with petrol, you don't encounter non-compact group, right? So it's not so common. So I think at the end you will agree that I have justified that it's some odd story. It is not conventional thing. Okay. So although I'm retired, but still, you know, so this is some commercial break for you. You can ask questions when this commercial is shown to you. Because I don't have any promotion or anything. So this commercial is first. Beneficial. Okay, so you can ask questions. Yes. Yeah. There's I don't know which symmetry exactly you use, but there's some matter bounds going into inflation symmetry. Yes, yes. You can tell you privately what is that paper. It's in the commercial. You have to go to supermarket to buy this. And then another one. Oh yeah, this one. Venetian one, yes. And then another guy. Good. Yeah. What do you think me to be? So you see, this is my not original thing. Either you understood everything, the seminar was very good, or it was so dumb that you did not understand anything. Yes. Could you please tell us about the society in which you were talking about physics here? Which string? This societal implications of string theory. No, societal in the sense, hey, well, one paper we wrote and also handwritten paper, societal application is this. That after that, there is kind of an industry, okay? So I don't know. There was a time for a couple of years, lots of paper were written. You take a metric, okay, and you look at the isometries and choose your this ODD group, okay, you generate. Okay? So you start with a spherical symmetric solution, you go to axially symmetric solution, then you generate charge. but then all these things. So that is the application to the industry. Therefore, it has social, you know, yeah, 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 nothing academic. You are so young. You see, you write paper, then somebody else cites your paper, then cite, and then when you apply for a grant, you have 80 times getting a grant. Then for your promotion. I'm sure if they're a very smart guy, somehow he'll come to the solar panel. Since the generating backgrounds used, but this is a completely non-automatic thing. In some sense, yes, because as I told you, because a gauge transformation, a general coordinate transformation, cannot take you from one to another. So there, in the technical language, there are distinct string vacua. So by perturbation theory, you cannot go from here to there. Yes. Let me ask the general kind of question. Is, is there any physical motivation for uh, the dimensions to be compact? Oh, well, you see, first of all, this is, well, since you were asking a philosophical question, I also see, first of all, there cannot be, today's world, there cannot be accessible 10 dimensions, okay? Right? So because there have been these attempts to have the radius of compact dimension uh, is large. Large in the sense the radius lies in the sort of scale of the LHC. That means when you produce those convergent states, they will be in the vicinity of TeV, right? So, but I know the numbers also. Atlas and CMS, they have to take it seriously. Uh, because they have put bounds that mass of these particles that to be greater than 2 to 60 because they cannot actually determine. Because I got interested in this. So last year there was some meeting of CMS. So they asked me to give a talk on my work. So I know. So that is out. At one time, people thought that they have solved everything. So let's say uh, 20 years ago, but that is how. So, we are living in four dimensions. Okay. So what is the thing? So there are more sophisticated compactification. Toroidal compactification is not the best. In fact, it has defects. It has some defects. But the other ones, but still, this question remains: that what is the radius of compactification? What is the radius of the internal space? No, you see, the question which I'm asking is, could there be a thing that you say that the physical field, and of the, yes, yes. Among all the fields, you say the gravity is the one only which should be open to propagate in other dimensions. Yes, yes. So can we physically say, for example, there was this year, what, not membrane, what is brain world signal. Ah, yes, yes. Where there was some physical motivation to say that yes, yes. The zero mass propagation, yes, cannot go deep into the hydra. Yes, yes. So the question is whether are there any such similar the physical motivations to swear. You are right. People around that time they got very deeply. They took it very seriously, as you say, that some energy, okay, disappear into this extra dimensions. Okay, so you find in some production processes missing energy. So I think there are some 8,000 papers have been written on this, or maybe more various scenario. Okay, that. But then you see on this side, you must have some evidence when you observe in detectors. Okay, You must have some evidence. Yes, we expected this to happen, but then what you say that this missing energy went to the internal direction. Okay, so there is no such. Yeah, particular Atlas and CMS have all this, but they can put only bounds. They don't have numbers. So what are the next scales and what can flow down? Oh, well, as I told you, you can make it inverse so far as this compact dimensions are concerned, in general sense. It is about say 2 to 6 TeV. Okay, TeV. You see, TeV. So you have to put dimensions to make it, let's say, TeV. So because you see, let's see, operates at let's say 13 TeV. Okay, so the protons are colliding. So each proton carries 6 TeV, roughly, okay? 6.5 TeV. So you can see back of the envelope, they can actually probe smaller length scale than that. But these are limits, you see. There is, I know for sure in CMS, there is a group called EXO group. Tomorrow, if you write a paper, you may put in the archives, actually proposing a scenario, at least some people in that, they will not discard it, okay? They will try to prove. Okay, maybe 2, 3 people, but they will try to prove what is the consequence of this fellow is saying. So this is called exo group. Okay, so their job is just doing this. I mean, various exotic physics that is proposed. Okay, so of course they can discard it easily in the sense they prove and say, no, no, this doesn't work. No, this is what. We are very far. Right. अरे भाई क्या बात कर रहा है टीवी का बात कर रहा है टीवी वो 10 to the 16 टीवी हाँ yes, yes. I hope the medical I told this in short in my last slide. I said I hope the medical science improve and I can still see your detections. Okay. So yeah, yeah. Yes. No, but you said what other theories? Not okay. Okay. Sorry. But if you go for vulnerabilities, anomaly is a very big thing. And these types of anomaly. So you see, you have to construct a theory if you come out. Okay. So that will be function. So, so vulnerability built in field theory. Okay. With the address of the field for code right? So I don't know the actual important work. But if you could change this, right, and then we try to feel for it. So people don't think the thing, you speak from the mind. For example, suppose we put a diagram electron, okay, and then let's see how so that we put ready. Now, suppose we say we are getting only taking a with probably two of the picture. So that can be better. You zero economy now, but you know, you take quantum connection with quantum. I'm not going to see one of the spectacular things, another that's okay, this is what so sometimes it needs some of the music actually currently. So already is that these things. I'm saying, you think I'm not doing that like I'm getting everything, but how extreme things. Right? So like one is going to do it, then get good, then we can continue. Like three, three of them, but you have the nothing. Can you see all these theories are varied? Okay, the gravity that the ground line, it has the most waves. You see, so and you see, we are short. You get the for mathematics for use. Okay, only get group with the responsibility to put the responsibility. So they are get three rules. That is why we are started thinking. So it comes to the other comes to part of the system, which we don't really have evidence for in that sense. We don't evidence for ground bonds. Well, there should be kind of sure and but that is the challenge people say. Oh, no, that's crap. Some people were this anyway. For things. This is what working over key transfer. This is basically passing. This is any other question? If not, let's go over to T. Come on. Bye bye. इसको निकाल मेरे से दोनों निकाल दोनों निकालना चाहिए इनका टेंडेंसी पास अवे चलो हो गया मुझे गुड गुड